Okay, so our next unit is looking at power and polynomial functions, okay, and we're talking about the characteristics. So a lot of what we're going to do today is stuff that we've already done. We're just putting it with a new function, okay? We have a little bit of new information, but most of it is repeat. Okay, so a power function, sorry, put your name on it just in case you lose it. Okay, so a power function is where we have x to the whatever power. Okay, so x to the first power, x to the second power, x to the third power. Okay, oh, actually they use an n instead of a b. That's an n. Can you tell that's an n? Yeah. Thank you for being sweet, but no, you can't. Let's try. We're gonna make it an n. That probably makes it worse. Whatever. Okay, so anything to the n power. So it does include linear because that would be x to the 0 power, right? Or x to the first, oh, sorry. Constant is x to the 0 power. Linear is x to the first power. Okay, the only restriction here is that a can't be 0 because if we have a number in front of this, then the whole thing goes away and it's no longer a function. And n can't be, well, n can't be 0 either. Pretty sure that's what it says. For a power function. Oh, yeah. So anything where you see x to a power. Okay. All right, so just a reminder, we have monomials. Mono means one, so all of our functions today are just going to be a single term. Okay. Next time we're going to look at polynomials where we have more than one term, and don't freak out about this. This is just like a really ugly math way of writing. You have more than one term. Okay, but it'll be like this. Like this is polynomial, right? Poly meaning many, right? Versus mono meaning one. Okay. All right, so all of our different functions that we've talked about so far, we have constant where our function is just a number. They usually use the letter C for that, for the word constant. And that's just going to be a horizontal line. Y equals 2. Y equals -7. Okay, horizontal line. Nothing fancy about that. See, I told you.
Teachers and students, please pardon this interruption. We are setting up for the panoramic picture for seniors, and we have a car that's close to the field house, a Nissan Rogue, license plate MSR6429. If that is your vehicle, they need it moved. It's blocking the area for the panoramic picture. So it's a Nissan Rogue, license plate MSR6429 gray. If you could move that car for us so we can get finished and get started before the rain hits. Thank you.
Before. All right, linear. Linear is, our function is just x, okay, or any transformation of that, right? We're not talking, this is just parent functions right now. We're not talking about moving them around any, okay? It's going to go through the origin, slope of 1. All right, quadratic is the x squared. It makes a parabola. When you draw this parabola, I want you to intentionally draw it wide, and there is a reason for that. Which I will explain in just a minute. Okay, so when we talk about other powers over squared, like when we do algebra 1, right, it's linear and quadratic, period. Okay, so then in algebra 2, we talk about cubic, we talk about square root, but there are all sorts of exponents and all sorts of powers that are further than that, right? So instead of just doing x to the second and third, we could do x to the fourth, right? So that's called quartic, is x to the 4th power. So if our function has the highest power as being x to the 4th, it's going to have the same shape as a quadratic because they're both even exponents. Okay, it's going to have that same shape, but it's going to get skinnier. And then if we did x to the 6th power, It's still even. It's going to be a parabola. It's going to be skinnier and get skinnier and skinnier and skinnier, right? As that exponent gets higher. Does that make sense? Okay, so all even exponents make this parabolic shape on the outside, right? When we talk about stuff next time, sometimes there are going to be like little squigglies like in between it, right? Like it might have some hills and valleys and stuff in the middle of those, but the ends of it are always going to go up there. Okay, and then same thing with our odd exponents. Once we start with cubic to the third power, we have this sort of half parabola going up and then half parabola going down, and sort of make that one wider. And then when we do x to the fifth for quartic, it's going to be that same shape, just skinnier. Okay, so it still makes that, I don't even know what kind of shape you would call that. Have a name? Whatever. Okay, so 3, 5, 7, 9, etc. They all have that same shape along the outside. Okay. All right, symmetry. We talked about symmetry before. If a function has an even power, okay, it is going to have symmetry around the y-axis. If the function has an even power, so all of our parabola-shaped graphs, okay, we are going to have, it is symmetrical about the y-axis. So even has symmetry along the y-axis going from side to side. And then if our function has an odd exponent or an odd power, so 1, 3, 5, 7, etc., it is symmetrical about the origin. So, reminder, okay, you can rotate 180 degrees and it'll be the same, it'll stay the same, right? That's your rule for symmetrical or symmetry about the origin. If you take your paper and you flip your paper upside down or rotate 180 degrees, the graph should look exactly the same. Okay. And remember, this only works when it like stays like along the y-axis, right? As soon as we move this parabola and we shift it to the right, it's no longer symmetrical about the y-axis, right? Because it's moved off the side, okay? Or same with our cubic function. If we move that sort of starting spot away from the origin, then it doesn't have symmetry about the origin anymore. Okay, so today we're not doing any translating. Okay, so all of that is what we've done before, right? Okay, so here is the only new part for today. Okay, and we've already talked about end behavior, but there is a pattern to end behavior of power functions, okay? So this is what I'm going to use my highlighter for. So if you have a highlighter or you would like a highlighter, these are your rules that are sort of hiding right in here. Anybody need a highlighter? I will throw one at your face. I mean, I would never do that. That was totally on the recording. I am walking to hand out a highlighter.
This is gonna be yellow. It's a close. This is my favorite one.
You're welcome. Okay. I have pink and blue. Okay. Okay, so these are the rules for end behavior. And end behavior was one of the things that people, like, it sort of struggled to wrap our brain around it because it's a little different than anything we've done before. Okay, so here's the rule. If you have an even power, 2, 4, 6, 8, as your largest exponent, okay, and the term in front of that is positive, okay, for example, positive x squared, could be positive 7x squared. It could be positive 35x squared, okay? Or x to the fourth or x to the sixth. Your end behavior, okay, it's always going to make a shape of a parabola, and it's going to be going up. So your end behavior is going to be up on the right and up on the left. Up, up. Sort of like a field goal, right? So when you have x squared and it's positive, it's always like this, goal, okay? Both ends are going up. So the way we write that, as x approaches positive infinity, okay? This way is positive infinity for our x values, okay? And then, we're good, thank you. As x heads towards positive infinity, our function is going up. So f of x heads up towards infinity. The notes are over there. Okay. And the calculator. So that's always the right side. We always start with the right side first when we write end behavior. Okay. And then on the left side, as our x values get smaller and we move off this left side of the graph, if I wanted to find this function, I would have to go way up to wherever it would be up on that side. So as our x gets smaller towards negative infinity, our function value, the y value, is still going up. Okay. Okay. So field goal, both ends are going up, right? Raise your arms like that. Positive x squared, even power, okay? If it has a negative value in front of it, it flips our parabola upside down, right? It still has an even power, but it has a negative in front of it. So now, as my x's get bigger towards positive infinity, our function is going down. And on the other side, as our function gets smaller, it's going down as well. So both ends of our functions are going down. A negative in front and an even power. As x goes towards positive, our function goes down to negative. As x goes smaller to negative, our function goes down as well. Okay. So your arms are like the parabola. If you could raise your arms, this is positive, even power. Positive, and then negative, right? Positive, negative. Okay, the one that's really important, and I would encourage you, I know it's early and you're like, I don't want to move. Okay, I would encourage you to actually do the arm movement because it's going to help you remember it. Okay, and you're not going to have to look back at it. Hush, trust me. Okay, if I can remember it, I'm old. If I can remember it, you can remember it. Okay, so the next one is the one that's different. So when we have a odd power, that's going to be our cubic graph. Okay, and the cubic graph originally looks like this, right? This side goes up into the first quadrant, curves up this way, and on this side it goes down, right? So this is if that value in front is positive. Whatever number's in front of the x to the third or x to the fifth or x to the seventh or whatever, this is, if it's positive, it goes this way. So if it goes negative, it's just going to flip, right? Negative here starts up on this side and goes down on this side. Does that make sense? Okay. So even, positive, even, negative, positive, odd, negative, odd. Yeah? See? You can do like aerobics. Got it? Okay. All right. So on this side, it's going to go up, and this side, it goes down. So as our x's get bigger, that's off to the right, our function goes up towards positive infinity. And then on the left side, as our x's get smaller, our function goes down to negative infinity. I think I'm going to have y'all do a project and make a function dance to a song of your choice. I think it's going to be awesome. You're going to do great. I've never done it before yet, but we've already talked about it. There are a lot of them out there, like
This month,
absolute value.
How about we like
Oh, it's on now. I think that's going to be your final exam.
That's gonna be our final.
I think.
I will gladly fail the class.
All right, so if we have a odd negative, as our x's get bigger, our function is going down. So that's going to be towards negative on that side. And then as our x's get smaller, our function's going up, 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 up. Okay, so before you turn the page,
But you do the bottom one first?
you do the right side first. Because our x's are getting bigger as we go this way. As x's get bigger towards positive infinity, this is the way our x's are getting bigger, our function graph is going down towards negative. Okay, so what if we had 3x to the 10th? 3x to the 10th. So we look at the power first. This is a even number, so it's going to look like a parabola. They're both going to go the same way. So do they both stay up or both stay down? This number is positive, so they're both going to go up, up on both ends. Okay, what if I had negative 5x to the 7th? So we look first at the power. Are these going to go the same way or different ways? These are different ways. So they start like this, right? Positive in the first quadrant, down here. Is it going to stay that way or is it going to switch? This one's going to switch because this number in front is negative. So instead of being up on the right and down on the left, it's going to flip-flop and it's going to go up on the left and down on the right. Does that make sense? So check the power, check your directions. Okay, so let's do that on the back. So what I really think is, I think for the end behavior, you should try to do that without typing it into your calculator and then check your answers when you see the graph. Okay, try to do it without first. Okay, and then we do still need to put our equations into our calculator so we can do all the other stuff. Okay. All right, so this looks familiar, or should look familiar, like we've done this on lots of different functions, okay? So today we're looking at, we're gonna sketch a graph, domain range, x and y intercept, increasing or decreasing intervals, which gave some of us a little bit of trouble, so we're gonna talk about that again. Telling whether it has symmetry about the y-axis or the origin, or none. Discontinuities, what does that mean? Discontinuity means
There's a break.
yeah, there's like a break. So it's not a solid line from left to right. Like you have to pick up your pencil and jump over to the other part. Like a reciprocal graph has a discontinuity. You can't draw that all at one time. Okay, so just FYI for today, bless you, if we're talking about parabolas and cubics, are there any discontinuities? No. So our answer for today, as we're looking at these first types of graphs, we'll just write none because there aren't any for them. Okay, so we'll get to that. All right, and then for our end behavior, let's go ahead and do that because that's the part that takes a little bit of time. So as x approaches positive infinity, as our x's get bigger, f of x approaches, just put a blank because we're going to fill that in a second. Okay, so we're just going to go through and we're going to just sort of fill that in. As x goes to negative infinity, as our x's get smaller, off the left side of our graph, our function heads towards blah, blah, blah. Okay? Can you do that for all three of these? And we'll just write that part. That's like the part that takes the longest, sort of. It's just getting that part written out. So looking at our first function, the first function is right here. It says 3x to the 6th. So are those going to go the same direction or opposite directions? The ends of our graph are going to go the same way. Are they both going to go up, or are they both going to go down? This is positive, so this is going to be up, up. So right here, up is positive infinity for both ends of that. Okay. Can you do the second one? Negative 2x to the 5th. So think about whether they go the same way or opposite ways. And do they stay the original or do they flip? Do you have your answer? Yeah? So, do these go the same way or opposite ways? Opposite ways. So normally we go up on the right and down on the left. So does this one stay that way or does it switch? It switches. So it's going to go up on the left and down on the right. Okay, now the problem is that this first arrow, the one on the left, that's as x heads towards negative infinity, right? Because that's the left side of our graph as things get smaller. So as we head off the left side, this is going up. So this second answer is the positive infinity. And then as our x's get bigger on the right side of our graph, we said that was going down. So that's the negative. Okay, so the list is sort of backwards. Okay, last one. Negative 1/2 x to the 4th. X to the 4th means same? Up or down? Down. Both down? Down. Okay. So I would like for you to try that without graphing, okay? Because I have a feeling when we could do like a really quick little quiz and just write that out. We could bust that out pretty quick. Okay, so let's grab our calculator. Let's graph this 3x to the 6th power. All right, 3x to the 6th power. Here's our parabola. Okay, in order to sketch the graph, I need a few points from the table. So Control T. Our graph only goes to 8, positive 8, negative 8. So I need numbers that are not going to fall off of that. So probably not going to graph 192. Let's skip that one. So I see 3 points right here. I'm just going to put a little table off to the side here. Negative 1, 3, 0, 0, 1, 3. Okay. Try to get whole numbers. If there's no option for whole numbers, then you might have to graph a decimal. Whatever. It's just an estimate, right? It's just to give us an idea of where the graph is. But you do not want to just sketch the graph without putting a couple points on it. Okay. So we're going to put these 3 points, negative 1, 3, 0, 0, 1, 3. And then we draw our little parabola through it. Put arrows on either end. Okay. All right, so once we have that, we can answer all the rest of these questions. Remember, our domain is from left to right. So does our function stop as we trace from left to right, or does it go forever and ever? Forever and ever. Parabola goes forever and ever both ways, so this is all real numbers. Range goes from bottom up to the top. So if I start at the bottom of my graph and I go up, does that graph forever and ever go from the bottom of my graph to the top of my graph? No, it stops right here. It does not ever go lower than this point, right? So what is this y value? Where this dot is? It's 0, 0, right? So our y value is 0. So the lowest y value is 0. And our function, does it go up from there or down from there? up, so that's greater or equal. This is an arrow, bottom to the top.
Okay.
When you're talking about range, you always start at the bottom of your graph. I always say top to bottom because I'm sort of like, that's sort of what we're used to saying. We always say top to bottom. Bottom to top sounds sort of weird, but that's really what you need to think of. All right, x-intercept, just trace along the x-axis. Where does our graph hit the x-axis? It's at the origin. I think for today they're almost all going to be at the origin because we're not moving them up or down any. Same thing along the y-axis. Hits at 0. Okay. Tomorrow we're going to shift our graph around and we're going to move them, so those will change. Okay, increasing and decreasing intervals. When we talk about increasing and decreasing, we're only looking at x values. Okay, for our interval, we're only looking at the x values. Okay, so we are going to start at the far left of our graph. And this is the problem. Okay, so what happens is when I look at this graph, I see this has an up arrow. So our brain says there's an up arrow, so that means it's going up. But it's not really, okay? Because what we're doing is we're going to start right here at this far left side of our graph, and we're going to start tracing the graph. And as soon as I start tracing the graph, my marker goes down. So all of this on the left side here is a decreasing interval because I'm tracing down to this point 0, 0. Okay, so this decreasing interval starts at negative infinity because we said it goes forever and ever both ways, and it's going to decrease until it gets to 0. And then once it hits that minimum value, it's going to turn, and the rest of our graph is going to go up from there. So from 0 to positive infinity. Okay, so FYI, when you're doing increasing and decreasing intervals of a continuous function, like it has a domain of all real numbers, okay, your interval will always start with negative infinity. That's the very first thing you should always write down, okay? So start with negative infinity and then go to whatever number. Sometimes it goes forever, right, to positive infinity, and it never goes the other direction, okay? But what's always going to be wrong is if you have an interval and you put negative infinity over here, because this has to be the small number and this has to be your big number. So you're never going to have a number smaller than negative infinity. So never ever put negative infinity on this side. Never ever is positive infinity going to be on this side, right? So just things to keep in mind. All right, symmetry, y-axis or the origin. If I fold this along the y-axis, are the edges of that going to match up? Yes, because this is an even power, so this is going to have a y-axis symmetry, and it doesn't have any breaks in it, so just put none or no or something like that. Okay, so again, like 95% of this is stuff we've already done before. Yeah. Nick's already done. Okay. All right, so number 2. You remember how to get a new graph? Got to get rid of the table first, or new page. Control doc, get you a new page. All right, negative 2x to the 5th. Okay, check our end behavior. We said this end goes up and that one goes down. So grab a couple points, go to your table. Little points, not big points. Not graphing 64. So really this, knowing what the graph looks like, well, we already know what the graph looks like, but getting these points is really the only thing you're going to need your calculator for today.
We just do 3 points?
Yeah, you don't really need more than 3. -1, 2. Okay, and remember when we graph these 3 points, they look linear, okay, but we just have to remember that this is a cubic or a quartic function. So it goes curvy up on one side and then curvy down on the other. All right, so then we fill in the other stuff. The domain, x values. Does it go forever and ever left to right? Yes. Does it go ever? That was wrong. Does it forever go from bottom to top?
Yes.
Yes, forever and ever. So those are both all real numbers. X and Y intercept are the same. It crosses right there at the origin. So these are both going to be at 0, 0 for today. All right, then increasing and decreasing interval. Okay, remember, start at far left of your graph. Start at the far left and trace.
We need for all 12th grade students and teachers to please make your way to the football
Okay,
field.
hold on. Can we finish this and then I'm just going to turn the thing off? Okay.
We need to move
Quickly.
We are trying to beat the rain.
Negative infinity. Where did they say to go?
We need all 12th grade
Football field. Okay, so this goes forever and ever down.
football field. Thank you.
Does it have symmetry along the y-axis or the origin?
The origin.
The origin. If you flip your paper upside down, it's going to stay and look exactly the same. Okay. The only difference on this last one is that it doesn't have any nice whole numbers for graphing. Like it has 0, 0, and then it has like a 0.5 or a something like that, which is fine. Everything else stays the same. Okay. All right. Football field.